which is also informally the Onward Conference keynote, where I'm happy to introduce Richard Gabriel to you all. It's actually impossible for me to introduce Richard and list all of his influences on our community in the time I have. He was a major figure in the development and standardization of Lisp. He played a large part in introducing Christopher Alexander's pattern languages into programming. He coined the phrase, "worse is better." He has a PhD in computer science from Stanford and an MFA in poetry. He writes a poem every day, which is the scariest fact about him. He played warm-up for the Velvet Underground. He promulgated the use of writers' workshops in computer science. He's been heavily involved in this community in organizing and shaping OOPSLAW and SPLASH throughout the years. And he founded the Onward Conference. It's safe to say this community would not be what it is today without his works. So let's please welcome Richard Gabriel.
Is the slide on?
Yes.
Every time you hear or read a story, you should ask how reliable the teller is. I'm going to tell you how AI unfolded as I observed it. I am first and foremost an AI person. In this talk, I'll weave in my story as it relates to AI. Figure out whether you trust me as teller. The slides contain more material than I will talk about. Sometimes you'll see text in red. That's the only text you might want to look at during the talk. You have the slides, so read them at your leisure. After this talk, I'll give you the transcript. I was born in Haverhill, but grew up on a farm in Merrimack. Pentucket at that time was one of the worst high schools in the country, rivaling those in Mississippi. The next part is a long story. It started in autumn 1966 and continued through spring 1967. What I did, the consequences, and how I reacted and eventually recovered set the stage for the rest of my career and personality. It forms the basis of how you should judge my version of AI history. In senior year, we had to write a term paper, jointly supervised and graded by the contemporary civilization teacher and the English teacher. I chose for my topic the megalopolis, the giant city. Through the fall, I worked on it. In November, I was accepted at Northeastern as part of its early acceptance program. Back then, they took everyone. I had also applied to Harvard and MIT. In early December, I got what I thought was great news. A Harvard committee to assess student scholarship potential sent someone to visit me and my family. Feeling my oats, I decided to indulge my urge to write and planned to write a preface to the term paper to make concrete the abstract things my paper said about the megalopolis. I asked the teachers for permission, and they said no. But I could write a one-sentence dedication. So I wrote a 3,000-word, one-sentence dedication addressed to a typical resident of the megalopolis, battered by shallow culture, poor jobs, fast pace, and low reward, someone whose life is barely worth living and whose creative and living juices are throttled by the routine of surviving in a place crowded to near death. He is a man unfortunately trapped by the horrors of contemporary civilization and made less a man, less a person by his circumstances. I turned it in early. The English teacher gave me an A+++++++++. A followed by 7 pluses. The contemporary civilization teacher gave me an F, averaging to C-. Joe Sherry didn't stop there. He wrote a letter to the Harvard Admissions Committee, writing that I had neither ethics nor morals, that he and other teachers suspected I had cheated in school, that my destructive attitude would damage my likelihood of success at Harvard and hurt other students. Harvard did not accept me, and neither did MIT. I went on strike and failed each course that semester. This rebellious streak thereafter defined my personality and approach to life. I became a cynical and caustic critic, and whatever was expected, I did the opposite. As Feyerabend said, anything goes. And as Jonathan mentioned, we got better reviews. By the time I graduated from Northeastern, I was a so-so mathematician, an OK Fortran and assembly language programmer, and I had no clear idea about the rest of my life except that I wanted to try for grad school. I applied to the usual places for someone who thinks he has half a chance: MIT, Harvard, Berkeley, Wisconsin, and Minnesota. I wrote away for the Oxford application. All these were in the top 20 in mathematics back then, and predictably I was rejected by MIT, Harvard, and Berkeley. I studied the application for Oxford for a day or two, but I couldn't figure out how to fill it out. Effective filter, I guess. Wisconsin and Minnesota took me and offered teaching fellowships, but I had a girlfriend for the first time and she was going to school in Boston, so I had to figure a way to stick around. Harriet Fell joined Northeastern from MIT. She asked what interested me, and my inept answer prompted her to say, "Ah, you're into artificial intelligence. You should talk to my friend Pat Winston, who directs the MIT AI lab." And I did. And he let me sit in an office at the lab for a year, and when the first AI winter hit, he said, "You should talk to Dave Waltz, who just graduated and has taken a job at the University of Illinois, and maybe you can go with him." And I did talk to him, and Dave said, "Let's go to Illinois and build an AI lab." And that's what we did, or tried to do. The well-known Lighthill report triggered the first major AI winter in the early 1970s. Though a British report, it had an effect on DARPA and then on me. Lighthill wrote, "In no part of the field have the discoveries made so far produced the major impact that was then promised." What is an AI winter? Funding for AI research and development dries up, though usually not completely. AI companies, if any there be, do worse or go out of business. News outlets, social media, and the public generally are down on AI. University research funding drops but doesn't go away. Funders tend to be fans of particular researchers, like McCarthy and Minsky. New projects arise and new people join, and eventually new breakthroughs restore AI's luster. A new spring. Lighthill blamed AI researchers for failing to address combinatorial explosion. Small problems might be solved, but real-world size ones wouldn't be. Back in 1972, PDP-10s were the computer of choice for AI labs. A large configuration had a 9 megahertz clock and 256 kilowords of 36-bit word-based memory, which translates to 1 megabyte. Why computer of choice? Most AI researchers used Lisp, and a PDP-10 address was 18 bits, which meant a Lisp con cell could be stored in a single word. Moreover, there were machine instructions to manipulate those half words, so in a sense, a PDP-10 was a Lisp machine by design. My computer at home today is 10,000 times faster and almost 200,000 times bigger and not shared with others. Naturally, we all knew back then we needed way bigger and much more powerful computers for real AI. Likewise, we knew that only toy problems were accessible. Lighthill broke AI into 3 categories. Category A was advanced automation, which addresses tasks where machines could replace people. His examples included OCR and pattern recognition. Category C concerns using computers to help come up with theories to interpret neurobiological data about specific areas of the central nervous system, using computer-based models of neural nets to test out particular hypotheses. Category B is building robots, that is, building devices that mimic a certain range of human functions. As of 2024, the 3 categories have blended, in large part because computer power has expanded the size and range of problems that can be addressed. 2 other important critiques of strong AI came out, one in 1972 and the other in 1980, but I won't talk in detail about them. They spurred quite a kerfuffle. Dreyfus argued that human intelligence and expertise depend on unconscious processes rather than conscious symbolic manipulation, and that these unconscious skills can never be fully captured in formal rules. Searle argued that if understanding or intentionality cannot be ascribed to a machine, then it is not thinking. It does not possess a mind in any ordinary sense of the word. Where did this criticism come from? Why such a strong impact? AI might as well have a kick me sign on its back. Unlike many problems computer scientists and programmers address, AI has an easy-to-understand goal, and the nature of success is vague as anything people try to do, as vague as success in painting, fiction writing, sculpture, music, composition, and poetry. Write a program that does things that usually only a person can do. Play a game, read a handwritten note, prove a theorem, write a program, transcribe a lecture, compose a sonnet, translate Madame Bovary to pitch and Jatjara, drive a car through the Mojave from Barstow to Prim, tell cats and croissants apart. What game and how well can the computer play? How long a note? How hard a theorem? Reminds me of Samuel Johnson's remark, which I'll revise. Sir, a program writing a sonnet is like a dog walking on his hind legs. It is not done well, but you are surprised to find it done at all. Back to the beginning. AI started in summer 1956 at Dartmouth College at a 2-month study proposed by John McCarthy, Marvin Minsky, Nathaniel Rochester, and Claude Shannon. Alan Newell and Herb Simon would make an appearance. The group was optimistic about what it could accomplish and how quickly. Problems reserved for humans and improve themselves, and a significant advance over 2 months in summer. In 1955, there were roughly no programming languages higher level than machine language and some simple so-called autocode languages, which were pretty much assembly languages. Even though the machines were computationally tiny, the main problem was seen as an inability to write programs that could exploit them. Human thought consisted of manipulating words using reasoning and rules of conjecture. We can see the origins of several AI threads in vogue today, neural nets and using randomness, including Monte Carlo methods. They were considering self-improvement, creative thinking, educated guesses, and hunches. Take a look at some of the words threading through the proposal. Imaginative, invention, discovery, uncertainty, failure, slightly wrong, unreasonable, unexpected, rough guess, originality, self-reference, learning. Even today, many would have trouble reckoning how to approach some of these. Newell and Simon set the stage for years of research. Because we don't even know what questions to ask, we shouldn't go for theories first, but instead build actual programs to understand and study. Some of you are too young to appreciate or even know how primitive computer science was in the early 1970s. Don Knuth published the first 3 volumes of The Art of Computer Programming in 1968, 1969, and 1973. There were few, if any, undergraduate degree programs in computer science. Given the vague goal statements McCarthy and his crew put together, progress seemed pretty good. Glance at this transcript of Joseph Weizenbaum's ELIZA program in 1967, whose most famous persona was a Rogerian psychologist. Now look at Ken Colby's Parry program, Chatting with ELIZA. Parry had a much more sophisticated language understanding model. Parry was designed to mimic a paranoid schizophrenic. In a lot of ways, Parry was a serious attempt at AI, while ELIZA wasn't. Take a look at this exchange and see how Parry is the better program. A group of experienced psychiatrists analyzed real patients and computers running Parry. When asked which were human and which were computer programs, they were correct only 48% of the time, a figure consistent with random guessing. Terry Winograd at MIT made the most notable advance in the early 1970s with SHRDLU, a program that used a simulated blocks world as a platform for a person to interact with a robot in English. This is a transcript. The person would see a display of the blocks and the actions of the robot. SHRDLU seems to understand what's going on and seems able to reason about the blocks world. Winograd produced 2 programming systems to implement SHRDLU. Microplanner is a backtracking theorem prover used for reasoning and planning. Programmer is for natural language understanding. As remarked by Newell and Simon, most of these achievements are based on guessing how to tackle the underlying problem. Many researchers at the time lamented the lack of computer power, which forced them to use toy examples, and so the idea that perhaps their guesses were off base wasn't top of mind. We, because I was in the AI crowd, were doing our best to dope out how to approach programming such ill-defined behavior. On top of that, the notion of mimicking human mental capabilities is an easy one to grasp, more so than, for example, appreciating the difficulties of tackling NP-complete problems such as satisfiability, and judging success seemed to be a matter of knowing it when I see it. And seeing just a little of it made it easy to believe that more was lurking just out of sight. CEOs and the military like the idea of cheaper, more effective, and more compliant non-human actors. Not surprising there was an AI winter. Trying to start an AI lab at the University of Illinois was not easy. To establish an AI degree program required passing a bill in the Illinois legislature. For me, this meant that getting a doctorate there was going to be tricky. I was in the math department, and their plan was dramatic. Take and pass all the tests required for a math PhD. Do research and write a dissertation in AI that satisfied both Dave Waltz and the math department. And because they were unsure about both AI and Dave, the dissertation had to satisfy 2 other folks, Marvin Minsky and Seymour Papert at the MIT AI lab. Herc. Dave Waltz was a favorite son in the EE department, and they had a plan. I'd take but fail all the required EE tests, and using a quirk in protocol, Dave and the EE chair would declare that I had passed. Then I'd do AI research and a dissertation that satisfied Dave Waltz, but I was still too starry-eyed to overlook the fraud. I decided to move on. I applied to MIT again and Stanford, the 2 best AI labs. Dave Waltz called in a favor with someone at SAIL, the Stanford AI lab, and I was whiteballed into the CS department. A white ball is the opposite of a black ball. I was put on the MIT waiting list. Don Knuth called to invite me to join him at Stanford. Who could say no? I talked McCarthy into my joining the Stanford AI lab in exchange for TAing his Lisp course. He was the worst teacher you can imagine, and just as bad at programming Lisp. I decided that despite McCarthy being at SAIL, they had a subpar Lisp, so I ported MIT's MacLisp to their PDP-10 and became the lab's Lisp wizard. I wrote lots of libraries and 2 Lisp programming environments. For my wife's master's thesis, I wrote a gate diagnosis program using expert system ideas. I didn't know much about computer science, so another student in my incoming class dumped a trunkload of papers and books at my house and said, "Read these and you'll know computer science." None of the 18 people admitted to the CS department that year had an undergraduate computer science degree. I took 4 CS courses, and the rest were reading and research and advanced volleyball. Look up Gabriel in the Hacker's Dictionary. Terry Winograd became my advisor, and I joined an automatic programming project to do their natural language generation stuff. The night before my oral exam, Terry called up and told me he planned to vote no. Not great news. But another student in my incoming class had helped me prepare my talk to an absurd level, something like 80 practice runs. So I passed without any grilling by the committee. He was also the bass player in my rock and roll band. My thesis system was called Yakety Hacks, but I've never revealed that before today. By the way, I designed and implemented a programming language to write it in, along with a soft description language. I did a lot of Lisp hacking, and became known for it. After graduating, McCarthy read my dissertation. Despite declaring it's not very good, he hired me to work on his revised advice taker project, where the basis of research was this statement: in order for a program to be capable of learning something, it must first be capable of being told it. The approach was to represent propositions in a formal mathematical language, and the interesting toy problems, as it were, require non-monotonic reasoning, the fact that the mere addition of new premises can invalidate a previously reached conclusion, something that cannot happen in purely deductive reasoning, something like this: all birds can fly. Canaries are birds. Penguins are birds. Slick is a bird. Can Slick fly? Yes. Penguins cannot fly. Slick is a penguin. Can Slick fly? No. McCarthy wanted us to use circumscription, his invention. We used a neo-Phragian approach. Around then, the Maclist community was split and drifting apart, and DARPA wanted to fund only one Lisp effort for their AI research. So I gathered the community, forged or forced compromises, and Common Lisp was born. After Common Lisp was designed, I started a Lisp company to implement it on stock hardware. It was a private label or OEM company. We provided Common Lisp to every workstation and mainframe company except Tektronix. And every AI company used our Lisp. In 1988, the second major AI winter hit. In the US, work on expert systems, simple planning, and logic-based reasoning overflowed into the business world, especially when AI researchers suddenly realized a lot of money could be made. The success of Myson spawned a raft of companies, mostly in California. The Japanese government launched a 10-year project to create a machine that could perform somewhere between 100 million and 1 billion logical inferences per second, a measurement they refer to as LIPS. Myson was an inference engine, and rules written like this one used an inference engine, and rules written like this one, which can be read thus: if the gram stain of the organism is gram-negative, and the morphology of the organism is rod-shaped, and the aerobicity of the organism is anaerobic, then there is suggestive evidence at the 0.6 level that the identity of the organism is Bacteroides. Here is a rule from my gate diagnosis program. Two things to notice. The rules go from observation to diagnoses, usually, and the force of the inference is a number. Critics of expert systems back then remarked that expert systems required you to program with floating point numbers, certainty factors, adjusting them until you got the right answers. Perhaps someone should tell that to NVIDIA. A certainty factor is a measure of how certain the system is of a statement. They range from -1, certainly false, to 1, certainly true. There is a calculus of combining them. When I started my Common Lisp company in 1984, like the AI company founders, I needed to convince venture capitalists to give me money, a lot of money. To get a lot of money without giving up most of your company, you needed to promise to make the venture capitalists a lot of money, redeemed at IPO. I recall working with my primary co-founder to come up with the most outrageous predictions of market sizes that didn't revolt us as scientists. You might say that we boasted of a bright future. Naturally, we were confident in our ability to create a good Lisp implementation on what was called stock hardware, but we depended on the hardware companies to make capable hardware and the AI companies to lure in customers. Therein lies the rub. AI systems are large and complex. Many were developed on Lisp machines, such as the Symbolics 3600, the LMI Catter, and the Xerox Dorado. These machines were designed and built by Lisp knowledgeable people, so the special performance needs of Lisp were handled by hardware. These machines were expensive. Could Sun workstations, for example, keep up? Dave Moon, arguably the best programmer alive in the 1980s, remarked that AI represented complex, ambitious applications that go beyond what has been done before. And what expectations do the AI companies hint at? Many potential customers had cadres of aging, knowledgeable experts at the hearts of their companies. And these companies heard that expert systems could replace those experts as they retired or were fired. The expectation was human-level performance for specialized cognitive tasks. The Lisp machines were indeed powerful and easy to program with for Lisp people, and I found out for those with expansive minds. My company was full of mathematicians and musicians, and even though with no Lisp background, learned quickly how to hack Lisp real good, as Rod Brooks once said. This was the early to mid-1980s. Hype, as we know now, derives in part from an echo chamber in which the same kinds of statements are repeated over and over. AI fundamentally draws people to overstate goals and performance, but along with that, many AI companies were led or directed by enthusiastic researchers who loved their own cooking and liked the idea of a big house on top of a South Bay hill with a view of Stanford. How lame were the people running AI companies? Around 1987, I met with Tom Kaler, the CEO of IntelliCore, to talk about my company helping his by tailoring and tuning our common Lisp so that their products could work better for our shared customers. He flatly refused. He said that my Lisp company had only one upward path, which was to provide AI systems in competition with IntelliCore, and that capitalism was based on non-cooperation. By the way, this is when Lucid, my company, was subleasing our offices from IntelliCore, a deal made because of the confluence of our business interests. Blame. As Supreme Court justices and undermotivated children prove, dogs and wives are to blame. The AI companies blamed Lisp for their failures. By 1987, there were plenty of competent Lisp implementations created by a variety of good companies and backed by strong hardware companies. AI from the 1950s through the 1980s concerned figuring out how to write programs people had no idea how to write to accomplish the vaguest of absurdly impossible goals. As McCarthy said, the problem was our inability to write programs. AI was about programming. Here is some programming stuff invented to cope with AI. Let's imagine the 1950s, the 60s, and 70s. You want to write a program that performs something intelligent a human could do. You aren't sure how to approach it, but you have some ideas. The computers you can access might have a megabyte of memory and perhaps 30 megabytes of disk space. They can execute 1 million instructions per second. Your choice of programming language is roughly these: assembly language, Fortran, Lisp, and COBOL. There are no libraries able to help. There are hardly any libraries at all. This is how things were until the mid-1970s. Any sort of help a programming system could provide came from something you created. In short, you or your colleagues needed to create the programming languages and surrounding infrastructure yourselves. When your goals are correctness and performance, you invent type systems, better compilers, and modularity, and you promote formal reasoning. When your goal is figuring out how to program something that many believe cannot be programmed, you invent mechanisms of expressiveness. Gaze upon some. This AI winter was a disaster for computer science. To see this, we must explore the idea of programming systems. Programming system is a platform comprising execution hardware at the lowest level, up through the interfaces to the outside world and to the programmer or user. It's a bottom to top to bottom system that supports programmers building up a system, starting with an already fledged and running system that supports reflection and self-modification. It is, in short, a live system. Lisp machines, Smalltalk, and roughly every Lisp implementation exemplifies programming systems. A programming system is not just a language and an operating system. Work on and with programming systems produce several important ideas, methodologies, and now common technologies. Some of them might strike you as unexpected, surprising even. My Lisp company and I noticed right away the business consequences of this AI winter. After I finished my poetry MFA in 1998, I saw that my research areas had been deleted by the Academy. And only in 2012 did I notice the demise of an entire way of thinking about programming and even computing. In the late 1980s, I realized that I had neglected my passion for writing. In 1993, I attended 3 writers' workshops and found out that actual poets thought I might not be bad. My computer science career became only a means to support my writing, something all my employers eventually noticed. In 1995, I started at an MFA program, graduating in 1998. I intended to resume my research career, but there was no interest in the work I wanted to do, nor were there any places to publish. I became a journeyman helper, helping Sun with some projects, including transitioning it to an open source company, working with marketing, and acting as a trophy to display corporate health to the outside world. I resented having no place to publish, so I helped design the Patterns conferences, the PLOPs, started Onward, expanded it to include essays, started the transition of OOPSLA to SPLASH, and helped design the art, science, and engineering of programming, all to create publication venues I could inhabit. Along the way, I became an expert in the work of Christopher Alexander. I wrote a couple of books, ran a couple of interesting conferences, and gave a handful of interesting talks. Around 2013, I happened upon a research project that combined my interest in writing and creativity with my knowledge of AI, Inkwell. We can ignore its origin story and focus on what I made it. An exploration of how creative writers, especially poets, think about and go about revision. Poetic revision goes way beyond conveying facts, meaning, and information. It's about connotations, sound, rhythm, lyricism, mood, attitude, voice, and subtext. In 1948, Alan Turing described how intelligent machines could come about. The machine, software mostly, would need both discipline and initiative. Discipline comes from programming, which I take today to mean the symbolic AI stuff, reasoning and actual thinking. Initiative might come from programming, but Turing hinted that one could start with an unorganized machine, a neural net perhaps, and teach it discipline and initiative. Most AI work until the 1990s was symbolic AI, or programming. Since then, machine learning has taken over. At least that's what the press, public, and Wall Street believe. These days, we're impressed by ChatGPT and other large language model-based systems. They can answer questions, write short essays and articles, and even write some programs with aplomb. We are so impressed by these abilities, we are beginning to worry about our place on the intelligence spectrum. But long before these generative feats, computers using non-symbolic techniques could do some amazing things, and in many ways, things that could be called superhuman. We'll start with genetic algorithms. The idea is simple. Simulate natural evolution with mechanisms for breeding, mutation, crossover, and selection. I use genetic algorithms for some things in Inkwell. If you're worried now about generative AI, you should have panicked in 1997 when Adrian Thompson's group did an experiment to evolve an FPGA to distinguish between two signals, a 1K square wave and a 10K square wave. They used a 10 by 10 section of a field programmable gate array, but without a clock. The FPGA was inside a Faraday cage because they had discovered that the genetic algorithm liked to design a radio in the FPGA to pick up the controlling computer's clock. Here's a diagram of the essential part of the evolved cell topology. Without a clock, it's an analog circuit. It worked very well. Thompson and his colleagues tried to figure out how it worked. Best I know, they never did. Here are some strange things about the circuit. The training evolution process used an actual FPGA. When a different physical part is substituted for the one trained on, the circuit doesn't work well. If you make the circuit in the diagram with CMOS, it doesn't work. If you simulate the circuit with one of the commercial simulators, it does nothing. The function units of the red cells are not used by the circuit, but when those units are clamped, that is, their function units set to return a constant 0, the circuit doesn't work. Ignore the upper left-hand cell in the diagram. The remaining red cells are used only as routers, that is, they are essentially wires in the circuit. The upper left-hand red cell, though, is particularly interesting. It is not directly connected to the active part of the circuit at all. Yet if its output is clamped, the overall circuit doesn't function. Most intriguing behavior is how the circuit gets the answer. The right answer is gotten 200 nanoseconds after the trailing edge of the first high waveform, which means that whatever interesting that's happening is happening when the waveform is high. But as far as anyone can tell, absolutely nothing is happening in the circuit at that time. When the input goes high, the feedback loops in parts A and B are cut, and therefore those parts of the circuit revert to digital logic and become static. Part C is observed to be static. When the input is high, the power levels are quiescent. There is no activity in the feedback loops. There are no short pulses or glitches anywhere. There is no thermal activity. There is no RF activity, no response to RF. In short, no observation shows anything happening at all. Once the pulse falls, part A starts to ring with different frequencies depending on the length of the pulse. Parts B and C then turn that into the final output. In 1999, in a paper in CACM, Adrian Thompson described these observations like this. This is astonishing. This is hard to believe. Somehow, within 200 nanoseconds of the end of the pulse, the circuit knows how long it was, despite being completely inactive during it. We still do not understand fully how it works, and artificial evolution can produce bizarre circuits that work, but do we need to understand them? Genetic algorithms and neural nets, they meet in neuroevolution. Neuroevolution evolves the topology of the neural network along with the weights associated with the connections and the rules that govern how the weights change over time. A tough pole balancing task is to balance two poles attached to a cart by moving the cart to keep the poles from falling, given only the cart position and pole angles. This clever solution works by using the recurrent connection to the single hidden node to itself to compute the derivative of the differences in pole angles, thereby figuring out whether the poles are falling away or toward each other. Without evolving structure, it would be difficult to discover such subtle and compact solutions. Starting minimally makes discovering such compact solutions more likely. Kenneth Stanley and his colleagues explored an evolutionary technique based purely on search for behavioral novelty. The idea is to ignore objective-based fitness functions and use only a measure of novelty. An individual is favored when it is different from previously evolved individuals. This enforces an increase in complexity, which is a key issue in evolutionary theory. Novelty search can solve several so-called deceptive tasks, such as difficult mazes, that is, evolve a neural net that is able to traverse a tough maze. Another experiment involved creating a biped that could travel the greatest possible distance from the starting location. Novelty search consistently performed better than pure objective-based searches, primarily because the novelty searches routinely discovered hip rotation. Simulated annealing works well because it exploits a kind of novelty-seeking search. When Inkwell was instructed to write a series of short poems based on the same prompt, it eventually came up with the doozy you see here. Machines and computers can perform many tasks typically associated with people much better than people can. The human record for solving Rubik's Cube is 3.13 seconds, set by Max Park in 2023. The robot record is 0.305 seconds, set this year by a Mitsubishi electric robot, both the mental aspect and actually twirling the cube. If we were to adopt the fearmonger's pessimism, there would be no reason for a person to ever play with a Rubik's Cube. The same way that nowadays, no one plays chess or Go, no one runs races, and Jeopardy is off the air. On to ChatGPT and generative AI. I'm not going to explain in detail how those systems work, except to point out that they are more sophisticated than many skeptics give them credit for. But I will say that when it comes to writing, their capabilities fall very short of what even modest but talented human writers can do. Their success depends on a few things. First is an astonishingly large training text. The second is a deceptively clever representation of word meanings. And the third is a transformer-style generation mechanism based on a complex attention mechanism. Word2Vec is a vector-based representation of word meanings, learned neural net style by optimizing the prediction of words in a moving text window. Basically, the meaning of a word is reckoned from the words that appears near it in real text. The vector has no inherent meaning. Its elements aren't, for example, other words. The idea is to locate words in a sufficiently high-dimensional space so that being near each other implies semantic closeness, and direction implies semantic category, more or less. Dimensions I've seen range from 100 to over 12,000. For example, let's compute the offset vector that joins the point representing man to the point representing woman. Then we'll locate a point that is that same offset from father and show the 10 closest words to that. Well, that's not too bad. But if you start with bull instead, it doesn't work very well. Very roughly and a bit inaccurately, a transformer takes as input a series of words or sentences, encodes the words with something like Word2Vec and positional information, and using a bunch of attention layers to figure out the ways various words relate to each other, spits out a series of words or sentences that are a response to the input. This response is based on predicting the next word in each sentence using meaning gleaned from the input in the sentences up to that point. The whole shebang relies on a Word2Vec-like representation of meaning because the next word prediction relies on shifting possible choices around based on multi-headed attention, shifting kind of like the man-woman shifts we just saw. But note that the examples I showed use Word2Vec representations of only 300. That's not great. ChatGPT uses a more elaborate and much larger multi-dimensional representation, sort of like Word2Vec, larger, like 12,288 instead of 300. There are a raft of neural nets used in the transformer and a pile of matrix multiplications. A big raft and a huge pile. I'm not a good enough programmer to judge how well ChatGPT programs, plus I can program only in Lisp. But I asked ChatGPT to explain this function. Wow, it figured it out. ChatGPT must be really, really good at staring at code and doping it out. This is better than many programmers I know can do. But wait. I took that function and changed the variable names to gensims, what theorists call alpha conversion. I started a fresh chat. ChatGPT was stumped. It seems to use a combination of surfacey reading of the source and staring at variable names to figure out the code. On the other hand, this is just what many programmers I know actually do. Getting back to writing, which I'm better at, I asked ChatGPT to write a short poem responding to these words: loud guitar blues music. This task was posed to Inkwell in 2015 by my now deceased colleague and bass player, Ron Goldman. Hey, man. The 3 ChatGPT ones are simply not very good, though one could forgive them were they written by high school students. I believe this becomes apparent when you compare it to the one Inkwell wrote, lower right. A writer colleague said of the third one, "There's a lot of cliche in the poem. The material is precious. There's no sense of concrete experience. Though the lines strive for metaphor, they fall short of finding anything fresh or specific. The excessive anthropomorphizing is a problem too." Nikki Ben Bourbaki is a pseudonym I used in the late 1980s, most notably in a series of debates between Nikki Ben and me in 2 different tech magazines on the topic of worse is better. I for, he against. Different LLMs do better or worse on this depending on whether they were trained on my website. Quite inventive. Then I asked ChatGPT to revise a first draft of a poem into prose, using its own voice and making it more interesting. The original poem is mediocre, but not incompetent. The writer colleague said of it, "The piece starts with cliché and generalized description and moves toward anthropomorphizing the city, but not in any fresh and original way. There's no real attitude or tone beyond a general one. We get some specific description. I'd say dust-covered crosses is the strongest, but the writer can't leave well enough alone and goes too far editorializing about what those crosses mean. The detail is already significant without having to explain. We are told there's a subtle humor, but the piece offers no sense of it, no experience of it." By the way, I used the expensive version of ChatGPT. Perhaps we can reason about it. People fear LLMs will replace human writers. In fact, LLMs are decently competent casual writers. They will not replace, for example, Cormac McCarthy. I believe AI will eventually produce interesting individuals, but LLMs are not that. One of my goals with Inkwell was to see how far a program with only language knowledge could go toward thinking like a writer. LLMs share this language-centric focus, but LLMs are built to explain using only what they were trained on what people tell them using prompts, and what a clever algorithm supplies as direction. Because of these limitations, an LLM cannot be an individual. While we're at it, perhaps we need to rethink the Turing test. Does it show that machines are human, or that humans are not so extraordinary? Real writing is about revision. I own and have read a dozen books teaching revision. I'd say LLMs are good at writing first drafts at high school level, term paper level. LLMs are good at explaining facts, but they don't seem to do well with words, their noises, their rhythms, connotations, loveliness, cultural nuance, point of view, voice, things I worked on with Inkwell. The poet Brenda Hillman told me, "When in doubt, make it strange." I had a weird thought. Is the reason LLMs seem so good also why they are not very human? A person cannot know everything, but has mechanisms for discovery and handling novel situations. LLMs don't seem to have those quite. The only experiences they have are those that have been written down, acquired during training or in prompts. An LLM has been trained on every point of view, so cannot have its own. Perhaps if an LLM were more limited, more ignorant, more illiterate, it could be a better writer or more like a person. Perhaps it could learn to forget. Robert Boswell, a good writer and great writing teacher, talks about an approach to fiction that nearly all creative writers know, a form of contemplation, a complex and incongruous way of thinking, working in half knowledge. While revising, the writer listens to what has made it to the page. The uninvited is often the most interesting. Unusual landscapes and strange desires emerge when the world remains half known. There can be no discovery in a world where everything is known. A crucial part of writing is remaining in the dark. Do I dare say it? Worse might be better. Any chance of another AI winter? Dunno. Depends on which AI you mean. Speaking only of LLMs and creating texts, the current value of ChatGPT is about the same as a decently talented, relentless 17-year-old, good at using Google, but a tad gullible. Irresistible business value, eh? But there is more to it. Recall the late 1980s AI winter that was a disaster for computer science. Its collateral damage was the near death of research on programming systems. The current mania over deep learning and LLMs is a disaster for symbolic AI. Without symbolic AI or something like it, artificial systems would be limited to what can be learned from large training sets. Without symbolic AI, AlphaGo wouldn't work, ChatGPT wouldn't work. Without symbolic AI, you can't create a program that tries a variety of classifiers and combines them to reach a novel conclusion. We would be unable to tell a system, advice taker style, that a certain kind of unicorn is a white goat-like animal with a long, straight horn with spiraling grooves, cloven hooves, and sometimes a goat's beard. Instead, we'd need to ask, where's the training set? Since the 1990s, some researchers have been promoting neuro-symbolic AI, which integrates neural and symbolic AI architectures to address the weaknesses of each, providing an expert system capable of reasoning, learning, and cognitive modeling. But if we are in a symbolic AI winter, if funding outside deep learning and LLMs diminishes, how long will we need to wait until the next symbolic AI spring? Thank you, good luck, and go well.
Hello. We have plenty of time for questions. There are 2 question mics set up, so please queue behind them, and we will round robin.
So Dick, thanks for thanks. Can you hear me? Thanks for a wonderful talk, and I may as well say it in public, since I'm making a fool of myself this conference asking questions. Thanks for all the stuff you've actually done. Some of which I appreciated at the time and some of which I didn't. My question is, and I think it is a question, for better or for worse, I've been doing a lot of work in Daphne and looking at some of the tools that the VMCAI and the formal methods people, or rather the formal proof people, are actually starting to use and starting to make usable. When I was in the 1980s, things like solving SAT was a problem that was considered the province of AI. Even questions like, where is this variable used in my Lisp system, was something that an AI system like the Programmer's Apprentice was dedicated to solving. I think this community, or part of this community, has actually made real progress on solving all those kind of problems, which I guess is where the symbolic AI might have gone. Do you think that's the case? And in particular, do you think there's any way in which, or have you any advice on how we might be able to get that out into the wider world? Because we can do things much more quickly and much more efficiently than LLMs can.
No, I don't.
Well, thanks anyway.
Right. Well, I'm going to, since I put you on the spot here in the first place, I'm going to continue to put you on the spot. So you have, decades of experience in how computer science works, and the ACM in particular, and you're influential in SPLASH and onward. So what's our next step? We need more places to publish, as was your driving motivation, and many of us are still driven by that, and we need to somehow increase the impact, or at least perceived impact, of these places. You know the politics of how this works. What's our next step?
Well, I think that the biggest stumbling block to Onward, Programming Conference, and other things is the passion that primarily academia has with indexing. That is to say, taking account of who has published what in how respectable a place, and then making funding and hiring and promotion decisions based on that. So somehow we have to get rid of that, I think. We are so enamored of monetizing work that there's little reason for people to work on things they're simply curious about. throughout my career, I've seen all of these only get worse. And so I'm fairly pessimistic, number one. Number two, because of my age, in some ways I don't really care what's going to happen next. You know, Onward is small, the programming conference is small. Looking outside of what Kuhn would call normal science in computer science and programming, et cetera, doesn't seem to be very interesting anymore. So, sorry. So it's up to you young people to fix it. So ready, go.
All right. Marcel.
Thank you again. Thank you again for the talk.
You're going to have to repeat these questions for me.
Because you can't hear?
I can't hear them.
Can you up the...
Yeah,
No,
the
it's
mic
not
is
so much that. It's
okay, I speak louder. When you returned from your MFA and found your research field gone at the university, you said, you had some strategies on how to proceed, right? How to stay motivated in the things that interest you. Do you have some advice if this happens today to people that want to push some directions? And so can you recall some strategies you did then, or did you reorientate and found some new stuff to do? Or did you manage to, well, find some creative way to keep doing what you like to do?
Yeah, we're like kind of in a weird anechoic.
well, we're in the bass. I hear only the bass of his voice. So what did he say?
So it was strategies for...
Yeah, when the university stopped funding the things you like to do, so deleted your research field, you did something to keep going. And if this happens today, were there strategies that you would still advise people to do?
So I kept doing things, but what I was doing was primarily helping other people with whatever they were doing. So I wrote a lot of essays, things like essays over the years, starting when my research area was deleted. And writing essays is not like doing research. I did research on the side. I did a whole bunch of projects that I've never published about, that I've never written about, that I've never spoken about to folks. So I'm different in that from probably most of the people here, not in a good way, but I just liked playing. And so the fact I had my own sandbox was good enough for me. There are some communities that I try to help, but I try to help them with writing, with setting directions, goals and stuff like that. And what I do, I don't recommend other people do. The other thing is, I always considered myself a writer from a very early age. And the detour into computer science was an accident. And being successful at it was only an ego-based thing for me. And I always fell back on the writing. So I'm not a good example for any of you. So don't do what I did. And it looks like none of you are, so that's good.
So, testing. Okay. So, I very much appreciate and like your description of ChatGPT as a very eager, slightly gullible 17-year-old with good access to Google and high speed. So, I have a question actually about that as opposed to a more specialized, a more expert, if you will, approach like Inkwell. So you talked about how obviously ChatGPT is very good at producing first drafts. It's not necessarily very good at the revision process or coming up with something high level. My question is, in your perception or in your work as a writer, do you see any benefit to what ChatGPT can do beyond what it's been used as so far, which is generally very fast, very cheap work to get stuff done very fast and very easily? That obviously has been recognized. Is there any other benefit to what ChatGPT can do beyond that in the field of art, particularly?
So it is good at doing not ridiculous first drafts of things. That's one. Two, sometimes you can throw it for a loop with prompts, and that's good. Third thing is some of the LLMs have a parameter that you can tell it to set, which is how wild and crazy to be. And so in the art world, it can be used as a tool to explore areas that you don't really know. So unfortunately, a lot of the LLMs are designed with the goal in mind of people want to find something out and they want to learn what the answer is or what the situation is or what the history is. And as a writer or as a poet, I want to have it tell me things that I never thought of, that very few people have thought of. And so when I was talking to Peter Norvig about that, there used to be a type of poetry called flarf. And flarf was using Google basically to find pages that had a series of weird, unrelated words together. And poets would take the summaries of what Google would produce, and that would be their first draft. So as they refined how good Google was at finding answers, it became worse at producing flarf. So I talked to Peter Norvig, and he said, yep, that was intentional, not that they wanted to get rid of the poets using the thing, but they wanted it to be good at explaining things. So there needs to be a version of LLMs that are for discovering new material. Also, the symbolic AI thing is important because you can't always get a training set to train on things. You do want to be able to tell it, you know, this is a definition. You can sort of do that, sort of not do it so well. I know a small number of actual writers who use the LLMs for doing first drafts and doing some stuff. By the way, the abstract and the two of my bios were written by ChatGPT.
Hi. Hi, yeah. Thank you for the talk. I very much enjoyed it. I guess this is maybe a twist on the previous question and also, again, maybe asking you to predict the future. So you showed that, you know, ChatGPT is really not a great poet, at least at the moment. I've read and heard about some people who have a dream that these AIs will automate a lot of the drudgery in our lives and will free up humans to spend more time on poetry and art and having more fulfilling lives. And I was just curious to get your perspective on that.
It could, as long as there's still a way to put food on the table. So for the people who have been freed up from doing boring work. I believe there's, even though there's a winter in effect for these folks, that the marriage of symbolic AI and the neural net stuff will create interesting individuals who were the political and governmental situation favorable toward it, could free up people to do extreme creativity, for example. I think it's possible that can happen. I think it's a political, governmental, societal type of challenge that we would face. So not much of a prediction, but I think that eventually, so with the FPGA thing, you think, holy crap, how did it do that? I think within 10, 20 years, we'll look at things that are the downstream versions of LLMs with symbolic AI and say, crap, how did it do that? So I think that would be good. That's what I've been trying to do in my for money career my whole life. So sorry.
What would you look out for to notice AI spring when it happens so that we do not look at it in retrospect? So did you notice this back then, or was it all like, oh yeah, this happened 10 years ago and we didn't notice?
So to clarify, when I noticed when or what?
Well, what were the signs? So the goal would be to notice it when it happens, right? As it happens. So when it happens, as it happens, that would be nice to notice. Oh, now is a good time.
Yeah.
We have an AI spring. What would you look out for?
It's sort of a secondary thing that I would look out for. So right now I've heard from one university setting that if you are applying to be a professor there in AI and you're not doing neural nets and deep learning, they won't hire you. So there's kind of like a choke or filter put on hiring. And when that choke and filter is relaxed, that's when a spring is occurring.
Thank you for the talk. My question is, how, as a student, do you learn about things that are not in vogue?
Could you repeat that, Jonathan?
Is this better? Okay. How, as a student, do you learn about things that are not in vogue?
Well, I'll tell you something that's sort of an answer to that, but you'll have to adapt it to what students do today. So, for writers and photographers, what they used to do back when I was probably your age is they would go to a magazine rack with a huge selection of magazines, and they would pick magazines they would never pick. And they would buy them and they would read them to see what people were writing, see what kind of photographs they were taking. Another way is they would go to a big magazine rack and they would pick the third row down and they would buy every magazine in that row and read them from cover to cover, look at the pictures from cover to cover. So it used to be with Google and other things, you could kind of get it to do that sort of thing, show me new stuff. YouTube has a show me new stuff sort of thing. So I do that with YouTube. I try to throw it for a loop and show me tutorials in areas that I don't know. So you have to kind of use randomness to pick and choose, go to other conferences, go to, if more things become sort of open publication style, then just reading some parts of the other conferences in other disciplines is a useful thing. So that's what I've always done, and that's my only answer.
Thank you.
Okay, I'll ask you the final question. Is winter coming?
Well, so there is the symbolic AI winter, and there's already reports by investors of, well, there's an awful lot of money being thrown into this. Are we ever going to get it out? I think that people are going to realize that the current sets of LLM type things have limitations that it's hard to get around. So I think there's going to be an AI winter for the deep learning part, and maybe the symbolic stuff will come up a little bit. And I think we're at the very beginning of I'll call it neural net AI winter.
Okay, well, finally, I want to personally thank you. I wouldn't be standing here today if it wasn't for the things that you've done for the community. And I'd like to invite everybody else let's thank Richard Gabriel.